Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The dawn of the 20th century witnessed the nascent stages of radio, a realm teeming with both promise and frustration. Signals, often faint and elusive, struggled to traverse the ether, their whispers barely audible amidst the static and interference. Early radio receivers, crude and inefficient, demanded substantial antennas and relied on the operator's skill to discern any semblance of a message. The very essence of radio communication, its potential to connect across vast distances, was hampered by the fundamental challenge of amplification. Edwin Armstrong, a name synonymous with innovation in radio technology, stepped into this landscape, and in doing so, reshaped the very foundations of wireless communication. Armstrong's early genius manifested in his invention of the regenerative circuit, a breakthrough that offered a dramatic leap forward in receiver sensitivity and efficiency. The central problem Armstrong addressed was the inherent weakness of radio signals after traveling great distances. These signals, barely detectable, required a method of amplification far superior to the rudimentary techniques of the time. Existing receivers, dependent on spark gap transmitters and crystal detectors, struggled to amplify these weak signals effectively. The regenerative circuit provided a solution, a revolutionary approach that amplified signals by feeding a portion of the output signal back into the input. This positive feedback loop, carefully controlled, allowed the receiver to amplify signals many times over, effectively boosting their strength to audible levels. The mechanics of the regenerative circuit were elegant in their simplicity and profound in their impact. The circuit utilized a vacuum tube, a device recently developed, to amplify the incoming radio signal. A portion of the amplified signal was then fed back to the input, reinforcing the original signal and causing it to be amplified further. This regenerative feedback, when properly managed, created a cascade effect, dramatically increasing the receiver's sensitivity. Armstrong's innovation allowed for the detection of signals that had previously been undetectable, opening the door to clearer and more reliable radio reception. The circuit's ability to amplify signals, combined with its ability to act as a detector, represented a significant advancement over the existing technology. The immediate impact of Armstrong's regenerative circuit was nothing short of transformative. Radio receivers, once cumbersome and inefficient, became smaller, more sensitive, and capable of receiving signals from greater distances. The improved sensitivity allowed for the reception of weaker signals, leading to a significant increase in the range and reliability of radio communication. This innovation fueled the rapid advancement of radio technology, paving the way for the widespread adoption of radio broadcasting and communication. The regenerative circuit, in essence, democratized radio, making it accessible to a broader audience. The rapid adoption of Armstrong's invention, however, was quickly followed by a series of legal battles, a testament to the transformative power of his work. The patent for the regenerative circuit became the subject of intense litigation, a legal maelstrom that would consume Armstrong for years. The most prominent of these disputes involved Lee DeForest, another pioneer in radio technology. DeForest, who had also been working on vacuum tube technology, claimed to have invented the regenerative circuit independently. The ensuing legal proceedings, marked by conflicting claims and complex technical arguments, dragged on for years. The courts, at various times, ruled in favor of both Armstrong and DeForest, creating a confusing and protracted legal history. The complexity of the legal battles obscured the fundamental importance of Armstrong's contribution. The courts, grappling with the intricacies of the technology, struggled to definitively assign credit for the invention. The DeForest lawsuit and the subsequent legal wrangling illustrated the high stakes involved in the race to control this burgeoning technology. The impact of the regenerative circuit extended far beyond its immediate application in radio receivers. The principles of positive feedback and amplification that Armstrong pioneered found applications in a wide range of electronic devices. The core concept of feeding a portion of the output back into the input became a fundamental design element in countless circuits, from amplifiers to oscillators. The regenerative circuit, therefore, was a foundational building block for the entire field of electronics. The immediate adoption of the regenerative circuit by other engineers and manufacturers is a clear demonstration of its efficacy. Radio manufacturers quickly recognized the advantages of the regenerative circuit and incorporated it into their receiver designs. This widespread adoption led to a rapid improvement in the quality and performance of radio receivers. The regenerative circuit became the standard for radio receivers, propelling the industry forward. The legacy of Edwin Armstrong's regenerative circuit is undeniable. The invention addressed a fundamental problem in early radio technology, providing a solution that revolutionized wireless communication. The circuit's ability to amplify weak radio signals, its impact on receiver sensitivity, and its widespread adoption by the industry solidified Armstrong's place as a visionary in the history of radio. His work laid the groundwork for subsequent advancements, including his own invention of the Superheterodyne receiver, which built upon the principles of amplification and signal processing. The regenerative circuit stands as a testament to Armstrong's ingenuity, a demonstration of how a single innovation could transform an entire field. The amplification achieved by the regenerative circuit presented a new set of challenges, particularly as radio technology rapidly evolved. While it significantly enhanced signal strength, it also introduced issues related to selectivity and stability. As radio broadcasting expanded, receivers needed to differentiate between a growing number of stations, a task made difficult by the tendency of regenerative circuits to oscillate and interfere with other signals. Furthermore, tuning across a wide range of frequencies proved cumbersome and often unstable. Armstrong, ever the pragmatist, turned his attention to these limitations, recognizing that a more refined approach was required to truly unlock the potential of wireless communication. His solution, the Superheterodyne receiver, represents a pivotal moment in radio engineering. This design addressed the core problems of selectivity, sensitivity, and stability in a fundamentally new way. The Superheterodyne principle at its heart involved a process of frequency conversion, shifting the incoming radio frequency signal to a fixed, lower intermediate frequency, or RF. This conversion offered several advantages. By amplifying the signal at a consistent IF, engineers could design highly selective and stable amplifier stages, something difficult to achieve across the wide range of incoming radio frequencies. The architecture of the superheterodyne receiver is elegant in its simplicity and effectiveness. The incoming radio frequency signal first encounters a radio frequency amplifier, improving the signal strength. Then, the signal is sent to a mixer, a crucial component that combines the incoming radio frequency signal with a signal generated by a local oscillator. This local oscillator, a key element of Armstrong's design, generates a stable, tunable signal. The mixer combines these two signals, producing some difference frequencies. The difference frequency, carefully chosen to be the intermediate frequency, contains the original audio information, but at a lower, more manageable frequency. This intermediate frequency signal is then amplified by a series of highly selective IF amplifier stages. These stages are tuned to the specific IF, allowing them to effectively filter out unwanted signals and noise. The amplified IF signal is then passed to a detector, which extracts the audio signal. Finally, the audio signal is amplified and sent to a loudspeaker. The superheterodyne receiver, therefore, uses frequency conversion to move the incoming signal to a frequency that is easier to amplify and filter. The innovation lay in the strategic use of frequency mixing. The local oscillator's output, meticulously chosen, created a constant offset, converting the incoming radio frequency to the intermediate frequency. The EF, a fixed frequency, could then be amplified with exceptional selectivity and stability. The beauty of this design was its modularity and ease of optimization. The IF amplifier stages could be designed to perform optimally at a single frequency, rather than having to deal with the complexities of tuning across a broad range of incoming radio frequencies. This approach significantly improved the receiver's ability to separate desired signals from unwanted interference, a crucial factor as the number of radio stations increased. Consider the practical implications. Early radio receivers often struggled to separate closely spaced broadcast signals. The superheterodyne receiver, with its superior selectivity, could distinguish between stations with far greater precision. Furthermore, the increased sensitivity of the superheterodyne design allowed for the reception of weaker signals, expanding the range of radio broadcasts. This meant that listeners could enjoy clearer reception and access a wider variety of programming. The impact of the superheterodyne receiver was immediate and profound. It transformed the landscape of radio technology, quickly becoming the preferred architecture for radio receivers. The design was readily adaptable for different frequency bands, making it suitable for both shortwave and longwave reception. The superheterodyne principle's inherent advantages made it a standard for both commercial and military applications. Armstrong's work drew inspiration from the heterodyne principle, first demonstrated by Reginald Fessenden. Fessenden's experiments with heterodyning, which involved mixing two radio frequency signals to produce a beat frequency, laid some of the groundwork. However, Armstrong recognized the potential of this principle and refined it, developing a practical and efficient receiver design. The key improvements included the use of a dedicated local oscillator, the careful selection of the intermediate frequency, and the design of highly selective IF amplifier stages. These refinements were critical for the superheterodyne receiver's superior performance and widespread adoption. The influence of Armstrong's superheterodyne receiver extended quickly, impacting the industry. Companies and engineers recognized the advantages of the design, and it was rapidly adopted. The Radio Corporation of America, or RCA, a major player in the radio industry, quickly embraced the superheterodyne design and incorporated it into its products. This widespread adoption drove further advancements in radio technology, with engineers refining the design and improving its performance. The superheterodyne receiver became the dominant architecture for radio receivers worldwide, a testament to Armstrong's foresight and ingenuity. The design's impact is still felt today, given that the superheterodyne principle remains the foundation of virtually all modern radio receivers, from the simplest AM/FM radios to the complex wireless communication systems found in smartphones. The superheterodyne receiver continues to provide the necessary selectivity, sensitivity, and stability for reliable wireless communication. The legacy of Armstrong's work extends beyond radio, influencing the development of a wide range of electronic devices and communication systems. The widespread adoption of the superheterodyne receiver, a testament to Armstrong's innovative genius, spurred a period of rapid advancement in radio technology. Yet, even as the quality of radio reception improved, a persistent problem continued to plague the burgeoning industry: the pervasive presence of static and noise. Amplitude modulation, the prevailing method of transmitting audio signals, proved exceptionally vulnerable to these disruptions. Static, originating from atmospheric disturbances, electrical interference, and other sources, would invariably blend with the desired audio signal, resulting in crackling, hissing, and a significant reduction in audio fidelity. This inherent weakness of AM radio created a significant challenge for broadcasters and listeners alike, hindering the full potential of this revolutionary medium. Armstrong, ever the meticulous engineer, recognized the limitations of amplitude modulation and embarked on a quest to devise a superior system. He understood that the core issue resided in the very nature of AM, where the audio signal's information was encoded in the asterisk amplitude asterisk, or strength, of the radio wave. Any extraneous fluctuations in the wave's amplitude, whether from the intended signal or unwanted noise, were indistinguishable, leading to the corruption of the transmitted content. His solution, a stroke of brilliance, involved a radical departure from the existing paradigm: frequency modulation, or FM. The concept of FM revolved around encoding the audio information within the asterisk frequency asterisk of the radio wave, rather than its amplitude. In this new system, the strength of the radio wave remained constant, while the audio signal's variations were mapped onto corresponding changes in the wave's frequency. A louder sound, for example, would cause the carrier wave's frequency to shift more significantly, while a softer sound would result in a smaller frequency deviation. This fundamental shift in approach offered a profound advantage. Any amplitude variations, such as those caused by static or noise, could be effectively filtered out, leaving the frequency information and thus the intended audio signal intact. The intellectual foundation for frequency modulation was laid earlier by the British engineer John Rancher Clausen. Clausen, in a groundbreaking 1922 paper, had explored the theoretical possibilities of FM, demonstrating its potential for reducing noise. Armstrong, however, took Clausen's theoretical groundwork and transformed it into a practical, functioning system. He meticulously addressed the engineering challenges inherent in FM, developing the necessary circuitry and techniques to both transmit and receive signals using this novel modulation method. Armstrong's approach involved a complex interplay of several key components. At the transmitter, the audio signal was used to modulate the frequency of a radio carrier wave. This modulated signal was then amplified and transmitted via an antenna. At the receiver, the incoming FM signal was processed through a series of circuits designed to extract the frequency information. The receiver's design was crucial for achieving the desired noise reduction. Armstrong employed a limiter circuit to remove any amplitude variations, and a discriminator circuit to convert the frequency variations back into the original audio signal. To demonstrate the superiority of FM, Armstrong constructed an experimental broadcasting system. He set up a transmitter and receiver, allowing him to directly compare the performance of FM with that of AM under identical conditions. The results were, to put it mildly, striking. In the presence of significant static and noise, the FM signal emerged remarkably clear and intelligible, while the AM signal was rendered virtually unlistenable. This demonstration, publicized through technical papers and demonstrations, provided compelling evidence of FM's potential to revolutionize radio broadcasting. Armstrong's FM system provided a substantial leap forward in audio fidelity. The reduction in static and noise resulted in a cleaner, more enjoyable listening experience. Furthermore, FM's inherent ability to handle a wider range of audio frequencies facilitated the transmission of high-quality sound, including the full spectrum of musical instruments and the nuances of the human voice. This improved fidelity proved particularly advantageous for the transmission of music, opening up a new era of high-fidelity radio broadcasting. The development of FM, however, was not a simple technical triumph. The radio industry at the time was deeply invested in amplitude modulation, and many companies were reluctant to embrace a new technology that required a significant investment in new equipment and infrastructure. Armstrong faced considerable resistance, including skepticism from established broadcasters and manufacturers. The initial response to his invention was, therefore, cautious, marked by a mixture of admiration and apprehension. Despite this resistance, Armstrong persevered, convinced of the inherent superiority of his creation. The eventual acceptance of FM was a gradual process, driven by the undeniable advantages the technology offered. As the public grew accustomed to the improved audio quality and reduced interference, the demand for FM receivers began to increase. The development of more efficient and cost-effective FM transmitters and receivers, along with favorable regulatory decisions, further accelerated the adoption of FM. The Federal Communications Commission, or FCC, played a pivotal role in this process, eventually allocating specific frequency bands for FM broadcasting and establishing technical standards to ensure compatibility. The transition to FM was not without its challenges. Early FM transmitters were often limited in power, resulting in a shorter broadcast range compared to AM stations. Furthermore, the initial cost of FM receivers was higher than that of AM receivers, which could have deterred early adopters. These challenges were addressed over time as the technology matured. The development of more powerful transmitters increased the broadcast range of FM stations, and mass production led to a reduction in the price of receivers. The legacy of Armstrong's FM invention is profound. It established the foundation for modern high-fidelity audio broadcasting. FM radio remains the standard for high-quality audio transmission, providing listeners with a superior listening experience compared to the limitations of AM. The principles and techniques Armstrong pioneered continue to be employed in modern FM systems, demonstrating the enduring brilliance of his engineering. The impact of Armstrong's frequency modulation extends far beyond radio broadcasting. The fundamental concepts he developed, including the use of frequency to encode information and the techniques for noise reduction, have influenced the development of a vast array of modern communication technologies. From cellular phones to satellite communications, the principles of FM are used to transmit signals efficiently and reliably. Armstrong's invention, therefore, has not only transformed the way we listen to music and receive information, but has also played a crucial role in shaping the modern world of communication. The relentless pursuit of innovation and his unwavering belief in the potential of his ideas stands as a testament to Armstrong's remarkable contributions to the field of electrical engineering. The story of Edwin Armstrong, a narrative of innovation and technical brilliance, is tragically interwoven with a series of protracted legal battles. These disputes, born from the very nature of his groundbreaking inventions, cast a long shadow across his career, ultimately contributing to the personal struggles that marked his later years. The legal system and the burgeoning radio industry proved to be a complex and often unforgiving arena for Armstrong's genius. The first major legal entanglement concerned the regenerative circuit. Armstrong, in the early years of the 20th century, developed this revolutionary amplifier, a device that dramatically increased the sensitivity and selectivity of radio receivers. This innovation, capable of amplifying weak radio signals, significantly improved the range and clarity of radio communication. The problem arose, however, from the simultaneous, independent invention of a similar technology by Lee De Forest. De Forest, a pioneer in radio technology, had already established himself as a prominent figure in the field. The legal battle that ensued, a contest over the very essence of the regenerative circuit, became a protracted and costly affair. The core of the dispute centered on the question of priority, who had first conceived and successfully implemented the regenerative feedback principle. The legal arguments, often highly technical, revolved around patent claims, experimental evidence, and the interpretation of complex scientific concepts. The legal system at the time presented significant challenges for inventors. Patent law, still evolving in the early 20th century, often struggled to keep pace with rapid technological advancements. The process of obtaining and defending patents could be lengthy, expensive, and uncertain. The burden of proof rested heavily on the inventor, requiring them to demonstrate the originality and novelty of their invention. Armstrong, a man of unwavering conviction in his ideas, found himself embroiled in a battle that would consume years of his life and drain his financial resources. The Klotz, grappling with the complexities of radio technology, often relied on expert testimony and technical analysis to understand the nuances of the competing claims. The Patent Office, tasked with evaluating the validity of inventions, faced the difficult task of determining who deserved credit for the breakthrough. The legal strategy employed by both sides reflected the competitive nature of the radio industry. DeForest, seeking to protect his own interests and capitalize on the growing market for radio receivers, aggressively defended his patent claims. Armstrong, equally determined to secure his rightful recognition, fought tirelessly to assert his priority. The legal proceedings were marked by extensive depositions, expert witness testimony, and the examination of experimental evidence. The Klotz, attempting to determine the validity of the competing patent claims, had to navigate a complex web of scientific principles, technical specifications, and legal precedents. The legal process, inherently adversarial, pitted Armstrong against DeForest in a relentless struggle for recognition and financial gain. The legal outcome, after years of litigation, proved to be a devastating blow to Armstrong. The Klotz, in a series of rulings, ultimately sided with DeForest, effectively invalidating Armstrong's patent on the regenerative circuit. This decision, a profound injustice in Armstrong's view, not only denied him the financial rewards of his invention, but also cast a shadow over his reputation. The loss of the regenerative circuit patent, a cornerstone of his early success, represented a major setback. The ruling, a harsh verdict for Armstrong, left him feeling betrayed by the legal system and disillusioned by the industry he had helped to create. The impact of this initial defeat was significant, both personally and professionally, setting a precedent for the challenges that would come later. Armstrong's subsequent legal battles, particularly the ones concerning the Superheterodyne receiver, further underscored the complexities and injustices of the patent system. The Superheterodyne, a revolutionary receiver design, offered significant improvements in sensitivity and selectivity over existing technologies. This design, which converts incoming radio signals to a fixed, intermediate frequency for amplification, became the standard for radio receivers for decades. The Superheterodyne receiver, a pivotal contribution to radio technology, was a major advance in the field. The legal dispute over the Superheterodyne involved the Radio Corporation of America, or RCA, a powerful and influential entity in the radio industry. RCA, a company with significant financial resources and legal expertise, challenged Armstrong's patent claims. The legal battle with RCA, like the earlier dispute with DeForest, was a protracted and complex affair. The legal arguments centered on the interpretation of patent claims, the prior art, and the technical specifications of the competing receiver designs. RCA, leveraging its extensive legal resources, mounted a formidable defense. The legal proceedings, a clash between Armstrong's individual genius and the corporate might of RCA, continued for years. The strategies employed by both sides reflected the high stakes involved. Armstrong, relying on his technical expertise and unwavering belief in the validity of his inventions, aggressively defended his patent rights. RCA, seeking to protect its market position and minimize its royalty obligations, challenged the validity of Armstrong's claims. The legal battle, a clash of titans in the radio industry, played out in courtrooms across the country. The legal arguments, often highly technical, required the courts to grapple with complex scientific concepts and patent law intricacies. The legal proceedings, a test of Armstrong's resolve, took a significant toll. The legal outcome, again, proved to be a source of profound disappointment for Armstrong. The courts, in a series of decisions, ultimately sided with RCA, invalidating Armstrong's patent on the Superheterodyne receiver. This decision, a further setback in Armstrong's career, denied him the financial rewards he deserved. The loss of the Superheterodyne patent, a second major blow to Armstrong's financial well-being, compounded a sense of injustice. The legal system, in Armstrong's experience, seemed to favor the powerful and well-resourced over the individual inventor. The impact of this ruling, a harsh verdict for Armstrong, was significant, further eroding his confidence in the patent system and the radio industry. The patent disputes, a recurring theme in Armstrong's career, highlight the challenges faced by inventors in the early 20th century. The legal system, still developing and often ill-equipped to handle complex technological disputes, could be a formidable obstacle. The nature of the radio industry, marked by fierce competition and the pursuit of profit, further complicated matters. The legal battles, a constant source of stress and financial strain, took a significant toll on Armstrong's health and well-being. The legal system, intended to protect innovation in Armstrong's case, often seemed to work against him. The legal battles, despite their personal toll on Armstrong, had a lasting impact. The patent disputes, a series of landmark cases, helped to shape the legal landscape of intellectual property. The legal arguments and court decisions, a body of legal precedent, influenced subsequent patent law and the protection of inventors' rights. The challenges faced by Armstrong, a cautionary tale, underscored the importance of strong intellectual property rights in fostering innovation. The cases, a testament to Armstrong's tenacity, also highlighted the need for a more equitable and efficient patent system. The legal battles, a complex and often tragic chapter in Armstrong's life, serve as a reminder of the challenges faced by inventors in the pursuit of progress. The legacy of these struggles, a combination of personal hardship and legal precedent, continues to influence the world of innovation. The Superheterodyne receiver, a cornerstone of modern radio technology, continues to function within nearly every radio receiver manufactured across the globe. Its architecture, a testament to Armstrong's foresight, forms the foundation for countless devices. The principle of frequency conversion, the heart of his invention, remains a standard practice in communications engineering. It is a ubiquitous element in television sets, radar systems, and countless other electronic devices. The enduring presence of this technology is a direct measure of Armstrong's ingenuity. The Superheterodyne receiver, a pivotal innovation, allowed for improved selectivity and sensitivity. It enabled the reception of weaker signals and the rejection of unwanted interference. The receiver's effectiveness, a critical advantage, fueled the rapid expansion of radio broadcasting in the 20th century. The other major invention, frequency modulation, or FM, further cemented Armstrong's legacy. FM radio, a superior method of broadcasting, offered significant advantages over the then-dominant amplitude modulation, or FM's ability to deliver clear audio with significantly reduced static and interference. A marked improvement transformed the listening experience. The reduction in noise, a key benefit, made FM particularly well-suited for broadcasting music. The wide adoption of FM, a cultural phenomenon, reshaped the landscape of radio. It fostered a new era of high-fidelity audio broadcasting. The impact of FM, a lasting contribution, extends beyond entertainment. FM radio, a vital component of public service, provides critical information during emergencies. The technology also plays a role in various other applications, including two-way radio communications and satellite communications. The legal battles that consumed much of Armstrong's later life, a tragic consequence, stand as a stark reminder of the challenges faced by inventors. The patent disputes, a complex web of claims and counterclaims, pitted Armstrong against powerful corporations. The legal system, intended to protect intellectual property, in this case, often seemed to work against him. The protracted litigation, a drain on his resources and emotional well-being, took a heavy toll. The struggle, a constant burden, ultimately contributed to his untimely death. The legal battles, a cautionary tale, highlight the importance of protecting inventors' rights. They underscore the need for a fair and efficient patent system. The lasting impact of Armstrong's inventions, a profound influence, is readily apparent in the modern world. His contributions, a fundamental element, shaped the evolution of communications technology. The regenerative circuit, the superheterodyne receiver, and FM radio, the core of his innovations, continued to influence technological advancements. His work, a source of inspiration, has guided generations of engineers and scientists. His legacy, a testament to his genius, endures in the devices we use every day. The superheterodyne receiver, for example, continues to be the basis for modern radio receivers. The design, a lasting influence, is still taught in engineering courses globally. The principles, a fundamental concept, form the basis for understanding more complex radio communication systems. The architecture, a foundational element, is a testament to Armstrong's understanding of radio frequency engineering. The superheterodyne receiver, a product of his innovative mind, is a vital component in countless devices, from consumer electronics to scientific instruments. FM radio, another of Armstrong's inventions, continues to thrive as a primary mode of broadcasting. The superior audio quality and resistance to interference, a significant advantage, made FM a popular choice for music broadcasting. The technology, a critical element, has also found applications in other areas, including emergency services and aviation. The impact of FM, a cultural force, is evident in the widespread availability of FM radio stations. The technology's continued relevance, a testament to its design, underscores Armstrong's foresight. The legal battles, a difficult period, left a lasting impression on the legal landscape. The patent disputes, a complex legal saga, helped to clarify the laws regarding intellectual property. The cases, a series of landmark decisions, established legal precedents that continue to influence patent law today. The challenges faced by Armstrong, a lesson, highlighted the importance of protecting the rights of inventors. The legal battles, a painful experience, serve as a reminder of the importance of a fair and efficient patent system. Armstrong's legacy, a complex mix of triumph and tragedy, continues to resonate. His inventions, a profound contribution, shaped the development of modern communication. His genius, a source of inspiration, continues to influence engineers and scientists. The injustices he faced, a painful chapter, serve as a reminder of the challenges faced by inventors. The enduring impact of his work, a testament to his vision, is evident in the technology that surrounds us. The superheterodyne receiver, a product of his inventive spirit, remains a critical component in countless devices. The concept of frequency modulation, a revolutionary advance, transformed the landscape of radio broadcasting. The legal battles, a difficult period, highlighted the importance of protecting intellectual property rights. Armstrong's legacy, a complex interplay of innovation and adversity, continues to inspire. His contributions, a lasting influence, have shaped the world of communications and beyond. The development of radio technology, a testament to human ingenuity, owes a significant debt to Edwin Armstrong. His inventions, a series of breakthroughs, revolutionized the way we communicate. His work, a legacy of innovation, continues to influence the world. The superheterodyne receiver, a cornerstone of modern radio design, continues to function within nearly every radio receiver. The FM broadcasting system, another of his achievements, delivers high-fidelity audio to millions of listeners. The challenges he faced, a reminder of the complexities of innovation, underscore the importance of protecting intellectual property. Armstrong's legacy, a synthesis of brilliance and adversity, serves as an inspiration. His influence, a profound impact, continues to shape the world of communications. The lasting impact of his inventions, a clear indicator, demonstrates his vision. The enduring significance of his contributions, a testament to his genius, is undeniable.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.